So let's talk about a concept that can be very frustrating to work with in practice, and this is thermodynamic versus kinetic products. So what I've got here is a conjugated diene, and I'm going to add HBr. And I could say, well, what are you going to make? And you have two options for me. You'd say, well, I'd add the HBr there, or I'd add the HBr there and all the different combinations. But there's actually a little bit more of a complication to this. Let's say I'm going to get addition across the double bond. And the first thing I'm going to have is I'm going to have attack by the double bond on the HBr. I'm going to have the H. And for a little while there, I'm going to have a carbocation. And if I do this reaction and I add the bromine, what I'm going to end up getting is this compound. So we have 1, 2, E5 bromo 3 heptene. So in this case, I have a 1,2 addition across the double bond. But here's the thing, if you see my video on allylic carbons, what you'll notice is that we can also further stabilize this carbocation through resonance. And if I get the resonance, now I have addition on this carbon. And if I were to add it, I would get this compound here. In the interest of time, I'm not even going to bother trying to name it. But you can see that these are different compounds. In this case, we have the double bond away from the bromine. In this case, we have the bromine and the hydrogen that were added separated by a double bond. So which one do we get? Well, to understand which one we get, we got to understand why they're called what they're called. So this is what's called the kinetic product. And in the kinetic product, we get a 1,2 addition. We get a bond addition just across the bond. In the 1,4 addition, so this is carbon 1, 2, 3, 4. In the 1,4 addition, we have a double bond separating the bromine from the hydrogen that was added. This is more stable, and this is what's called the thermodynamic product, meaning that if we had enough energy, we could make it. The kinetic product is what you get if you go really fast, meaning that you just kind of take what you could get instead of waiting and being patient. This is more accessible at low temperatures, meaning that at low temperatures, we're more likely to form the kinetic product over the thermodynamic product. And the reason has to do with activation barrier. To move this double bond through resonance takes energy. So if we're at low temperatures, the reaction is going to go slow, and it's going to kind of take what it can get. It's going to take this 1,2 addition. If we go to higher temperatures, we provide enough thermal energy to overcome this activation barrier to make this structure and get the 1,4 addition. So if you want to favor the kinetic product, go to low temperatures. You'll go slower just because you're lower temperatures, but you're going to be more selected to this 1,2 addition. If we go to higher temperatures, we supply enough energy to make this bond resonate. Make it pop over, and this will give us the thermodynamic product, which is more stable, but again, you got to go to higher temperatures to make it happen.